Hi everyone, today I brought a very interesting question from the topic of Doppler effect. The question says a source of sound having frequency 3.2 kHz travels along the straight path SA with a velocity of 198 meter per second as shown in the figure. A stationary observer O is at a distance of 250 meter from this path. So remember the observer is at rest. Calculate the apparent frequency heard by the observer when the source velocity makes an angle of 90 degree with the line joining the source and the observer. And we have to take the velocity of sound as 330 meters per second. So let me explain the question. Here is the observer which is at rest and source is moving along this path SA with velocity Vs. We have to find the apparent frequency heard by the observer when the source velocity makes an angle of 90 degree with this line joining the source and observer. So clearly this is not that position, right? Because here if I join the source and the observer, this line is not 90 degree with this velocity. When it will be 90 degree? Obviously when the source will be here, right? So when the source will reach here, its velocity vector will be perpendicular to the line joining the observer and source. So at this moment, we need to find the apparent frequency heard by the observer. Now I've seen many students doing the mistake of thinking, since this velocity of the source has no component along this line, therefore the apparent frequency will not change, meaning the apparent frequency will be same as the actual frequency. However, students, that is not correct. The apparent frequency will change, and let us see how it happens. Before answering the question, let us quickly revise the concept of Doppler effect as taught in class 11. So here is the observer and here is the source. This is the line joining them, and this VO is the velocity of observer along this line, and VS is velocity of source along this line. And the formula for apparent frequency is given by V plus minus VO divided by V plus minus VS times the actual frequency. Now, what is V here? V here is the speed of sound. Speed of sound in air. In air here means with respect to air. Now, what about VO and VS? Listen very carefully. VO is the speed of observer at the time of hearing the sound. At the time of what? Hearing the sound. Now, when we say this is the apparent frequency of the sound heard by the observer, it is obviously at some particular time, right? At some particular time, he is hearing the sound to have this much frequency. So at that time, whatever is the speed of the observer, that is VO. Now, what about VS? Well, VS is speed of source at the time of emitting the sound. At the time of emitting the sound. Now, which sound am I talking about? The same sound which is heard by the observer later. Why later? Because sound will take some time to reach from source to observer, right? Now, in order to convince you why we have to do like this, think of this example. Imagine I say the word how at time 10 a.m. and that moment I was having velocity 2 meter per second. Now you are so far that this sound how reaches you, let's say, after 1 hour. So you will hear this sound at 11. Now at 11 I produce another sound, RU, and that moment my velocity may be something else, right? I may be running faster, and that sound will reach you later, 11:40 I have assumed. Now tell me, whatever sound you heard at 11, that was how or RU? Obviously how, right? And that sound which you heard at 11, the frequency of that sound will depend on which velocity? The velocity 2 meter per second or 4 meter per second? Obviously 2 meter per second, because the sound which you heard at 11 was emitted by me at 10, and that time my velocity was not 4, my velocity was 2, right? So therefore students, when you are asked to calculate apparent frequency of the sound heard by you, let's say at 11, the velocity of the source that you should use is not the velocity of the source at 11, because that may be different, right? You have to use the velocity of the source which it had at the time of emitting that sound which reached you later, right? Of course, if you had constant velocity, then it doesn't matter. Now, when we solved NCERT problems, the velocity of the source was constant. So that time it did not matter whether you used the speed of the source at 10 a.m. or 11 a.m. It doesn't matter because the speed of the source was constant. However, if the speed of the source is changing, then you have to be very careful to remember that this Vs is the speed of the source at the time of emitting that sound which reaches you later, right? The next question you may be having is when to take plus or minus here and here. Well, that's very easy. Just remember, whenever source and observer approach each other, the frequency will increase, meaning the apparent frequency will be more than the actual frequency. And when they recede away from each other along the line joining them, when they recede away, that time the apparent frequency will be less than the actual frequency. If you remember this much, then it's very easy to decide whether to put plus here or minus, and same thing for this. So let's see in this example, you can see the observer is approaching the source, right? So since observer is approaching the source, this VO should lead to increase in the frequency. Matlab numerator should be more, and when will be numerator more? When you take plus, right? Similarly, the source is moving away, it is receding away. So because of this, the frequency should decrease. Now when will the frequency decrease? Because of Vs. When the denominator is more, then the frequency will be less, right? So here you have to take plus. Now suppose the source was moving this side, then how the formula will change? Well, now source is also approaching the observer. So frequency, because of this source, the frequency should increase. Therefore, the denominator should be less. So you should take minus. So that's how you can easily decide whether to put plus or minus. Now let's come back to the original question. Remember, the observer is at rest and the source is moving along this path. The question was to find apparent frequency of sound heard by the observer when the source is here, because that time its velocity is perpendicular to this line, right? Now tell me, when the source is here, let's say the time is 10 a.m. and at that time some sound is reaching the observer. We need to find frequency of this sound. Now do you think this sound was emitted when the source is here? No, right? Because whatever sound this source will produce at 10, that will reach here at later time, maybe 10:05 or maybe 10 past 0.001 second, isn't it? So whatever sound this will produce at 10, that will not reach here at 10. So clearly whatever sound has reached here at the moment the source is here was actually produced when the source was somewhere behind, maybe at 9:55 or maybe 9:58, whatever it is, isn't it? So students, you have to be careful that the sound which is reaching the observer when the source is here was actually produced when the source is somewhere here. So this is the initial position of the source. Now let's say it took time t for this source to reach here. Then during that time, the distance covered by the source will be speed of the source into time taken, right? And during that time, the sound from here also has to reach here. So the sound has to travel what distance? Speed of the sound, we are writing v into the time taken, right? Now, let's use the formula to calculate the apparent frequency heard by the observer. So as we know the formula, the apparent frequency is equal to the speed of sound which we know. And since the observer is at rest, VO is 0. So no need to write VO here. And here we need to write the velocity of the source. Now tell me, should I write the velocity of the source when the source is here or when the source is here? Obviously when the source is here, because whatever velocity we write here is what I told you, the velocity of the source at the time of emitting the sound which the observer heard later. So whatever observer heard the sound, that sound was emitted when the source was here, not here. So we need to put here the velocity of the source which it has here. Now you may think it has constant velocity, so we should use Vs only. No students, we should use only that velocity which is along the line joining the source and observer. So when the source was here, remember it had velocity Vs this side. So if I say this angle is theta, the component of this velocity along this line will be Vs cos theta. Vs cos theta. So we need to put here not Vs but Vs cos theta. Right? Now, what about the sign here? Well, since the source is approaching the observer, the frequency should increase. So denominator should be less. So I should take minus. Right? Now the next problem we have is we don't know what is the value of theta. So how to calculate this theta? Very simple. In this right angle triangle, we know this distance is VST, the adjacent, and we know the hypotenuse is VT. So if I write cos theta formula as adjacent by hypotenuse, my t will cancel. So cos theta will be Vs by V. So substitute here cos theta, which is Vs by V. And that will give you Vs square, right? So I can write here Vs square. Isn't it? Let's simplify this. Here, if I take LCM, this will be V. This will be V square minus Vs square times F naught, right? And this V will go in the numerator. It will become V square. Now what I can do, I can divide the numerator and denominator by V square. So dividing this by V square will give 1. Dividing this by V square will give 1. And dividing this by V square will give you Vs by V whole square times the actual frequency F naught. And that's the formula to calculate the apparent frequency, right? So now only calculation is there. Let's calculate this ratio first. So Vs is 198, V is 330, right? So 11 3s are 33, here 0, and then 11 1s are, then 11 8s are. Then 2 9s are, 2 15s are, and here 3 and here 5. So if I simplify, I will get 1 1 minus Vs by V is 3 by 5, square it, 9 by 25 into F naught. F naught is 3.2. So here if you take LCM, the 25 will go up. Then 25 minus 9 will be 16 into 3.2. 4 4s are 16, 4 0.8, 32 it will come, right? 3.2. 4 1s are and 4 2s are 8. Here point will be there. And 25 into 0.2 will be 5 kilohertz. So that's the apparent frequency, which is not same as the actual frequency, right? Now the reason why students say that the frequency should not change is because they compare the given problem with this problem. Now if you see this problem, this is the source, this is the observer, this is the line joining them, and here is a source which is moving in a circle. So at this instant, its velocity is Vs perpendicular to this line joining, right? Now here if they ask what is the apparent frequency, then we say here the apparent frequency is same as the actual frequency. There is no change here. Now why? Previously there was change. The reason is very simple. Whether you wait now or you wait later, you can see at every instant the line joining and velocity is always perpendicular. So since it is always perpendicular, whether you wait at 10 o'clock or you wait previous to 10 o'clock, 9:55, it doesn't matter. At every time, the velocity of the source is perpendicular to this line joining, and therefore the apparent frequency remains same as the actual frequency. But in the given problem, if you remember, here was the source and the observer was moving this way. So when the observer was here, this line joining was not making 90 degree with Vs, right? Only when it reaches here, that time it was making 90 degree with this line. So please understand, do not apply the logic of this to this question. Here the component of Vs along this line keeps changing, unlike here. Here the component of this velocity along this line is always 0. Whereas here there will be some component, and when the source reaches here, that component will change. So please understand, in this problem, though the velocity of the source is constant, the component of velocity along this line, which is important for Doppler effect, that component of velocity changes continuously, right?